Okay, in a previous tutorial I explained to you how to calculate a number. That number was what I call the heat loss coefficient, and that was a measure of, as I expressed it, how good your apartments are at losing heat. Now, it was a very easy thing to calculate, and I hope that the previous tutorial made sense. All that you had to do was to multiply the area of each surface by the U value of each surface, and adding all those numbers together gave you a total, what we call conductive heat loss coefficient for your apartment, or, put into English, a measure of how good your home is at losing heat. Okay, so I told you what my home was like, and my home has improved as a result of what I've done to it. So I want to now move on and tell you what that actually means in terms of energy. So the figure that we got for my home today was 128 watts per Kelvin. This watts per Kelvin, I want to just explain a little bit about that. So the Kelvin is what I want to talk about. What does Kelvin mean? Kelvin is effectively a measure of temperature difference. So that means if we take, say, temperature inside and temperature outside, most of us are going to be happy inside between a temperature range of, let's say, 17 as a lower and maybe 28 as a higher. Now, that's another issue in itself, but let's assume that that's a good range whereby most of us will be, what we say, comfortable. So this Kelvin has to do with temperature difference. That means what's the difference in temperature from outside to inside. So if we were to say that I had my apartment inside to 20 degrees, that was what I had the thermostat set at, and outside was minus 10 degrees, well then we could say there's a 30-degree temperature difference. Now the only thing is we actually measure temperature degree not in degrees Celsius but in kelvins. That's where the K comes in. We often talked about this figure called delta T, which means temperature difference. So we can say in this condition there's a 30-degree delta T between inside and outside. And of course, as outside warms up, then that delta T reduces. If it was only 0 degrees outside, then we can say there's only a 20-degree difference, or 20 Kelvin delta T. Or if, for instance, we say, well, actually it is 18 degrees outside and it's 18 degrees inside, well, then we can say there is no temperature difference, and therefore there's going to be no heat loss. So all of that is necessary to know, because if we want to get to this magic figure of just watts on its own, a rate of heat loss, just this W, we have to know what the delta T is, as in we have to know what the difference in temperature from inside to outside is. So it's very easy to do. All we need to do is to multiply this figure we got for each of our apartments, and in my case I told you it was 128.9 watts per Kelvin. I'm multiplying that by Kelvin, which is, as I say, this temperature difference. So 128.9 multiplied by 30 Kelvin, that's on a day that it's minus 10 outside and plus 20 inside. That's going to give us a rate of heat loss for my apartment, 3,867. What I've done here, and you'll see this in the Dropbox, is it's all set out for you. All you need to do is input, as I say, your heat loss coefficient that you will have figured out into there. When you put it into there, it will automatically do a few things. It will work out how that heat loss coefficient by this temperature difference, which I have figured out, gives you a rate of heat loss on that at that moment, and it will graph it for you in terms of those inputs. Now, if, for instance, Yasmina, I don't know what she is, she'll tell us soon, but if she had an apartment that was twice as bad as mine, and put in 300 there, well, it will work that out for her too. Now, the things worth noting, obviously things might change. Well, what if, as I say, it wasn't minus 10 outside, but it was 0 outside? If I change the outside temperature, then it will change the heat loss. Or, what if it was minus 10 outside, but I was willing to put up with 15 degrees inside? Both of those figures will make a difference in terms of my heat loss at that moment. Okay, so when it is minus 10 outside and it's 20 degrees in my home, That is the rate of heat loss from my home. Now, as it happens, I have a 5 kilowatt, 5,000 watt wood burning stove in my home. So you would think that that is more than enough to compensate for the 3,800 that is leaving my home. Now, in reality, if all my assumptions that I told you were true, that would indeed be the case. But the actual reality is that I'm losing a lot more heat than I've told you. I'm losing heat up the chimney. I'm losing heat because there's air getting into my home through various cracks, some deliberate, some accidental. And actually, I'm losing heat through other places, such as the floor, none of which I've taken into account in these calculations. So in fact, my wood-burning stove does a lot, but it doesn't do enough to keep my house fully warm, as indeed I hoped it would. So that is interesting, but the question of energy is the next thing we want to get to. How much energy does this all amount to? We know the rate at which I'm losing heat, but how much energy does that actually mean? Well, the key thing about energy is time. So if we know the rate at which I'm losing heat and we know how much time I'm losing it for, then power by time equals energy. That's watt hours. You've probably heard of kilowatt hours. Well, it's exactly that. So watts is what we just looked at as the rate of heat loss, and hours is obviously the measure of time. So we can do a very simple thing now. If we know the rate at which I lose heat, 3,867 watts in my case, when it's minus 10 outside, and if I know that's the case for 5 hours, as in it's always minus 10 outside and it's always 20 degrees inside, well then, if I have the heating on for that amount of time, I can tell you that it will be 19.3 kilowatt hours of energy that I will use in order to maintain that situation. So that's the same kilowatts that you see, kilowatt hours that you see in your meter, whatever meter you have in your home. It's probably measuring kilowatt hours. So again, going back to our spreadsheet, this time if we go a little to the right, we will see a next thing which has begun to be populated by the first thing, and it says, well, how many hours did you have the heating on for? In my case, I've said, well, it was on for 10 hours. Now, if it was on for 10 hours, then it's going to work out the heat loss that I had multiplied by 10 is going to give a figure of kilowatt hours. The other two, you don't need to do anything here. The only thing you might want to do is to change this figure in terms of how long you had it on for. But the other figures will calculate themselves, and they have to do with carbon. So let me say a quick word about carbon. Well, how much carbon does that mean? Well, I've said very quickly in the PDF that different countries produce energy in different ways. Ireland, we do it through peat. UK, mixture of nuclear and coal and that kind of stuff. Brazil do it all by hydro, and that means different things in terms of carbon emissions. But effectively, we can save ourselves a lot of bother and just understand through one of these institutions, such as the Carbon Trust, what each kilowatt hour of energy means in terms of kilogram of CO2. So I've taken those numbers and I've done your hard work for you and multiplied your energy total, which is the total of your time that you had the heating on, multiplied by the rate of heat loss, and I've multiplied those by the two carbon factors, and then that will give you the amount of carbon emissions that is associated for that amount of energy consumption, depending if your heating is from electricity, grid supplied electricity, or if it is from natural gas. Now, a kind of handy thing is, if you're brave, you can begin to build up a picture of what that actually means over a year. How would you go about doing that? You'd probably have to, I'm not going to do it now, but you'd have to understand that obviously the outside temperature in the month of January is going to change. So you might go about taking the average month of January external temperature, and then that would tell you a rate of heat loss for that external temperature based on your delta T. And then you would have to go and say, right, okay, generally in January I might expect to have the heating on, I don't know, let's say 8 hours a day or 6 hours a day, whatever I think it is. And then that would tell me how much energy it's going to cost me. And obviously the hours are for every 31 days of January. That would give you a figure. And that would allow you bit by bit to understand what your total energy consumption is likely to be, and then what your total carbon emissions are likely to be. So if you're feeling brave, you can try and quantify that as best you can over the course of a whole year.